The question that we've been asked to present on today is why matchsticks curl upward when they burn. So this is only true for horizontal matches. Vertical matches, when burned, will just sort of bend a little bit, arbitrary direction, and not nearly to as severe of a degree as you expect from a match that's burned horizontally. So the question naturally arises as to why. So we'll start with the background on the problem and establishment, and then move through what exactly the experiment we conducted was, data and analysis we drew from it, conclusions, and then some good research. So matchsticks are made out of a highly porous wood. How porous? This porous, extremely porous. And these pores are filled with a mixture of air and water vapor. And things you may know about air and water vapor is that they expand when they're heated. So we thought that this would be a good starting point for considering what may cause the curling of the match. The matchstick head itself is made primarily of potassium chlorate with some chalk mixed in to prevent it from burning up too quickly and failing to ignite the wood. So the ideal experiment that we would have liked to have done would be checking to see if temperature was proportional to the amount of mass that was lost. This would be a pass conundrum. Okay, stop, refocus. We would check to see if temperature is proportional to the mass lost. And if this was found to be a correlation that held true, we would then move on to seeing if the temperature was proportional to the amount that the match curled. The goal for this particular experiment would be correlation, not actually good solid causation, because there are so many highly random factors involved in the burning of the match. Simply establishing a strong correlative relationship is plenty of success. The reasoning that we're using is that the upper area of the match would burn hotter. And so, since this hotter burn would result in a greater amount of the mass of the match being lost, the area of the top of the match would decrease faster than the area of the bottom of the match. And since a match can be modeled as a rectangle, if we're to shrink one of the sides of a rectangle faster than we shrink the other side of the rectangle, the result would be a curve. So mass lost would indicate that we should expect an upward curve because the hotter part of the fire is removing more mass across the top of the match, which causes the top plane of the match to shrink faster than bottom plane of the match, resulting in what we would expect. Unfortunately, this experiment was not possible. We do not have good, effective tools to measure temperature, nor do we even have access to a scale that is able to measure with that level of precision. So we had to compromise. Our actual procedure was to A, burn matches so that we could get data, then photograph the matches, and then run photography-based mathematics on them so that we can establish whether the interior arc of the match, the exterior arc of the match, and the height of the total matchstick after the burn are correlated in any way with the angle that the match is bent. The idea is that if we do find that the arc length inner, arc length outer loss ratio is in fact correlated to the angle that it bends, we see that the inner arc gets shorter by the same amount. You might go, that's automatic. And go, it would appear to be automatic. And you would expect it to be. But if we do not find it, that would be automatically disqualifying to our theory. So it makes sense to check it. And the second thing that we're looking for is its comparison to the total height of the match to see if the greater end angle bent, to see if the greater amount of burn total, we just lost more match, you can see because the height would have decreased by more, would result in a larger bend and a larger difference in arc lengths. If that test was passed, it would indicate reasonably strongly a correlation between the arc length inside, arc length outside. So how precise were we able to be in the collection of this data? Not precise at all. We are looking here for only correlation, not actual precision. And furthermore, rather than trying to prove our hypothesis correct by establishing a solid relationship, we are simply looking to disprove our hypothesis by seeing if they are uncorrelated. In this case, we don't actually learn anything from a success. We only would learn things from a failure. We are, as the funnel that I have helpfully provided indicates, simply trying to filter good ideas from all ideas by getting rid of some of the chaff, rather than searching to find the correct idea itself. If you want another look at the data slide, you can see the angle arc length conversions. It's generally moving in an upward direction, but the change in angle over change in angle arc length, which is what you would expect to be constant, is not terribly constant. And even if we expected it to be inconstant, because we're going to say the geometric effect of the arc becomes more extreme the more that you burn, it takes less additional burn to bend further, you would expect it to be moving consistently in a downward direction, and that's simply not the case. So, what is the actual answer? Well, my esteemed partner here helpfully did some research and found the actual set of studies on the reason that matchsticks burn into curves. There's a function for energy, burn time, and the mass burn rate. But what's gained from all of this is the simple proposition, the simple explanation that when excited by the heat of the burn, the moisture and gases locked in the wood are released. That's why the wood shrivels up. Those porous chambers that you saw earlier are actually shrinking and crumpling up under the heat. This exerts pressure on the matchstick that is different than burnt wood and unburnt wood, and this causes the burn. The force that you would expect on the matchstick is the mass burn rate times the velocity of the escaping moisture and gases times the distance from the end times the angle that it's at. Thank you. And if you wanted to actually understand the equations provided here, here are the constants that are used and what the definitions that they are applied with are.